time seems to flow. It has a single direction moving through us, pulling the future into the past. British astronomer Arthur Eddington described this process as time's arrow, and it is this asymmetrical movement of time that drives the evolution of our universe. From its origin in the Big Bang to its predicted demise. We use the second law of thermodynamics to describe this process. Entropy, which we might call the level of chaos or disorder, has been constantly increasing throughout the universe since the Big Bang. That is to say that the universe is acting to equalize the distribution of mass and energy. And through this process, it has given birth to stars, the formation of galaxies, and the chemical reactions that gave rise to life itself. But it also brings with it death and decay. But what if this wasn't the case? Well, the universe as we know it could not exist. Without time's arrow, there could be no stars, no galaxies, and no life. And at the same time, there would be no death and no decay. The movement of mass and energy that sustained these could not take place. And therefore, entropy in its description in the second law is interesting because it helps us distinguish the past from the future. It provides direction for time's arrow.
What is time? A deceptively simple question, yet it is the key to understanding relativity. Is time universal? In other words, is there an audible tick-tock throughout the galaxy? A master clock, so to speak, forging ahead like Mozart's metronome? The answer, my friends, is no. Time is not absolute. In fact, for us believing physicists, the distinction between the past, present, and future is but a stubborn illusion.
The faster you move, the slower time ticks for you as others view it relative to the observer. You don't know anything's happening. Your clock still ticks as far, you still got your heartbeat, all of this. Okay? So this is not a physiological thing. It is an actual property of the fabric of space and time under those conditions. I watch you fly by, and the faster you go, the slower time ticks for you. Let me get a pair of twins. All right? They're born the same time, they're the same age. And now one of them, I will send off at 90% the speed of light. And the other I'll keep down here on Earth. So we can ask, how do their aging rates compare? Okay? Turns out, this twin that I've already sent, his clock ticks 44% as fast as this twin's clock. Our clock here on Earth. So, this twin is aging more slowly than this one. That's at 90% the speed of light. Let's pump it up some more. How about 99% the speed of light? Now the time ticks at only 14% the rate, as it does back here on Earth. How about 99.9%? We're getting closer and closer to the speed of light itself. And at that speed, the clock ticks only 4.5% as fast. So, what does this mean? Tell you what it means. This twin that traveled for 5 years and comes back, if they went at 99.9% the speed of light, after 5 years, they're 5 years older. We have aged 110 years. It's called the twin paradox. It's only a paradox if you think about it in sort of classical terms. How could that be? But in relativity, there is no paradox at all. That is a fundamental feature of what happens when all you do is presume that the speed of light is the same for everybody and the laws of physics remain constant. So not only does speed do this, also the strength of a gravitational field will have the same effect on you. The stronger the gravitational field is, the slower time ticks for you.
Clocks on the moon beat a little bit faster than clocks on the planet Earth. On Jupiter, clocks beat slower than on the planet Earth. The heavier the planet, the slower time beats. This means that on a star like the sun, time beats even slower. And the ultimate star, of course, is the black hole, the remnants of a dying star. We think that at the very center of the black hole, time stops.